All right. So, good morning, everyone. Thank you for attending our class. I know it's really early. Is this kind of a thing works for you, or do you prefer that I just record this ahead of time? You can just view it, and we'll keep the channel open so you can ask me questions. But there's like the video will be definitely shorter if that's the case because no one will ask me questions. But if this is okay, then we'll do this way. I thought it's nicer if you could ask live questions from me instead of just watching a video and then trying to ask me questions afterwards. Well, it still works for now. So we're moving ahead. We did normal distribution last time, so that was the most recent lesson. We're moving towards what we call sampling and statistical studies. But before that, there is one more component that we need to look at in terms of normal distribution, and that's standardizing. That should have been the title, actually. All right. We'll calculate, we'll review lessons about normal distributions. You can see here. And there might be new vocabulary along the way. But the important thing is we'll calculate area under the normal distribution, under the normal curve. So it's like specific amount of space of a shaded area, something like that. And that's it. We'll try to see if we can apply the breakout session today as well. So there aren't a lot of announcements. It's actually the same as last time. Module 10 is due March 22. So most of your readings are still in Module 10, so that's the goal of the class. As far as discussion board is concerned, it's Module 10. Also, packet check still suspended. Same thing about discussion boards. Miss your group quiz, let me know. And we're currently in mod. Can you hear me? Right. Script 2.
¿Eh?
It's also helpful if you temporarily mute your audio, unless you have questions. Okay, so I think this is mod 13 as of the moment. Okay, so let's take a look at some of the always, sometimes, never questions. Okay, so for the first one, given n our normal distribution with a mean of 10 and a standard deviation of the population being 5, then unusual values are between 5 and 15. That always, sometimes, or never. What do we mean by unusual values in the first place? Feel free to join me in my conversation here. So we know that the center will be mu equals 10. And we're spreading from the center 5 units. So this is the first standard deviation above the mean. So 10 plus 5 will give you 15. And
Never?
10 minus 5 equals 5. Is it a never? Let's see.
Because
Check that one.
unusual would be more than one standard deviation or more than two. Correct?
More than, yeah, beyond, yeah. More than 2. So let's do like another standard deviation marker there. And this will be a 0. So we are looking past these 2 standard deviations. So we're looking at this portion here for it to be considered unusual. However, we're given kind of like 5 and 15, which is 1 standard deviation, right? So that is true. That's a never. That's an error for that case. Okay, let's take a look at the second one. A normal distribution is symmetric, bell-shaped, and with the point of inflection coinciding the first standard deviation. So mouthful. All right, let's take a look at the normal distribution here. Um, let's break it down first. Is it symmetric, bell-shaped? So that I think is a yes. Pretty much what the normal distribution is. This is the unusual portion here. With a point of inflection that matches the first standard deviation. So if this is the mean and this is the first standard deviation, there is a point there. Okay. So it kind of matches. Can you mute that mic? All right. So yes, this is actually true. This is a point called the point of inflection. We do not focus too much on that, but it kind of separates the graph. The graphs uh, concave up, so it's called concave. It's like looking up, and then concave down, which is this part here. Yeah, so this is actually always true. All right. Okay, so let's take a look at the third one. The area under the normal distribution with a center of 12 and a standard deviation of 1.5 will have a bigger area compared to a normal distribution with a center of 10 and a standard deviation of 1.5. So will it be different? So if you have centered at 12 versus a normal distribution with a different center, a smaller center, will the area here be bigger than the area there? Well, they have the same, spread. So this is like 11.5, while this is 13.5. So this is not true. That's a never true, because it's not even a sometimes true. They always have the same center. They always have 100%. You know, you can have a very tall normal distribution or a very flat normal distribution. They both will end up 100%. It's, it's kind of like the balloon analogy last time. You can stretch the balloon, you can compress the balloon. The amount of water or air inside it will not change. It's just, whatever you put in it. Make sense?
Yes.
All right. Um, go to our next review. We're still in the review. So we talked about unusual and typical. Typical being one standard deviation above and below the mean. And unusual values was from the earlier example. They are values that are beyond two standard deviations. So if you have a normal distribution, the bulk of the data, majority of the data will be about 68% of them will be one standard deviation above. So this is kind of like the typical values. Now, if you move a little bit further away, you will get two standard deviation. That will be about 95%. Unusual values will be beyond them. So here. So they're extremely rare. They're very rare. Okay. Because 95% of the data are already here. So you're looking at those rare occurrences that is not part of the regular 95% of the data. Okay, so this one, just additional terminology. When you hear the word random variable, well, it's random. It's a result of it's coming from chance. or a chance event. But in the case of our lesson today, random variables will consider that those are quantitative variables. We'll consider a quantitative variable that you get from a random event or a chance uh, random variables. Okay, so for example, if you're selling some chocolates, uh, each customer will buy, a variety of number of chocolates. So those are random variables because you don't know how many a person would buy. You know, only that person would know. So it's kind of like random. Um, all right. Okay. So if you have your handbook with you, it would be nice to actually go along with me in this one. So look at the page 129, and we'll tackle what we call standardizing scores or standardizing values. Uh, just remove this. Remove that. Okay, there you go. All right. So in statistics, a standardized score is a distance measurement between the value that you have, that's your x value, and the mean, which is your mu. Um, and the way to measure them is through standard deviation. In other words, a standard score answers the question, how many standard deviation is the value from the mean? So when you standardize a value, for example, you have standard at 10, and then you're going up by 5 standard deviations for a standard deviation. And so this must be a 5 and this must be a 0. So here, the value x equals 20. That is two standard deviations, two sigmas from the mean, from mu, right? That's how far that is. So the z there is 2 because the z tells you how far the value is from the center or the mean, the center of the mean. Um, so when we convert x equals 20, that becomes z equal to. And we do have a formula for that. As you could see here, to get z, we need the value minus the mean over the standard deviation. So we have your x value minus your mu, your mean, your population mean, divided by your population standard deviation, sigma. So let's try that. If we use the same value, so 20 minus 10 over 5, because the sigma here is 5 units. That's the standard deviation over there. And we'll have here 10 over 5, which is 2 standard deviation from the center. So that's how we look at the standardized score. We look at it as a distance. How far is the value from the center of the normal distribution from here? Make sense? So we'll find out why we're using this. Most of the data, of course, will not have the same standard deviation, will not have the same center. But in some cases, we have to compare them. And it's good idea to standardize them because standardizing the scores will give you a more objective way to compare values, and not just looking at raw numbers for comparison. Okay, let's take a look at some examples to check our understanding of this. So this has to be part of the same chapter. Suppose that you took a test and scored 85 out of 100, and the average of the class mean is 75, and the standard deviation is 10. So That's so it's for you, your data are as follows. You got a score of 85, you got a mean of 75, and you have a standard deviation of 10. Okay. Now, for your friend, it's the same. Oh no, your friend took a test, so it might not be the same test because it's only 16 out of 20. And the mean would be 10. Okay. All right. So, if your mic is not mute, please mute it, so I won't have to compete with the sound on the background. But unmute it if you have a question, because I could hear the other sound. It's being recorded as well. All right. So your friend will have a score of 16. The mean is 10, and the standard deviation is 5. Okay. So who performed better? That's the question now. So which of the two scores actually is relatively better within their own groups, and amongst each other? It's hard to compare them because they don't have the same they don't have the same possible points. One is 100 and one is over 20, and they don't have the same center, they don't have the same spread. The best way to actually compare them is to actually look at how far they are from the center. Okay, so I think I can add. Can you please mute your mics? Okay, there you go. Okay, so let me copy the data. I think the first one is 85 for X, 75 for the mean, and 10. So 85, the mean is 75, and 10 for sigma. And we are comparing that with, I think the other one is 16, 10, and 5. And 5. Okay, so let's calculate how far the data is from their center. So the center here is 75, and the score is found here. Oh, that's not X. The score is found there, which is 85. Now we're looking at another normal distribution here, centered at 10, and this is 6 points away. This is kind of like 16. So let's calculate the Z to standardize it, to look at, looking at the same type of standards, putting them in the same type of measurement, like within a standardized measurement, which one of them is further away means they're kind of like higher than the other, relative to the other. So you have X minus mu over sigma, which is 85 minus 75 over 10. That's 10 over 10. It's actually 1 standard deviation. So this is exactly 1 standard deviation. The other one is you have 16 minus 10 over 5. That's going to be 6 over 5. So we know this is a little bit higher than um, 1. This is, I think, 1 and 1/5. So 1.2, if I'm not mistaken. So just correct me if I do some arithmetic error. So this is around 1.2 sigmas away. So the first standard deviation there will be here. So it's a little bit higher. Well, this one is right there. So even though it's only 6 points apart and this is 10 points apart, standardizing them will help us be more objective in comparing them, because this is further away from the center. This performance is a lot better. So your friend actually performed better. So your friend was the one who performed better. So we did compare the two of them through a scale, using Z through a similar scale, and we use standardized score or Z score to actually compare them. Okay. So who scored a higher percentage? A percentage scales both scores to a score out of 100, so that we can now easily compare the score, find the percentage to each of the question. Well, as far as percentages are concerned, let's see. The first one is 85 out of 100 versus 16 out of 20. So of course this is 85%, and 16 out of 20 is percent is that 16 divided by 20 is 80%. So score-wise, with respect to all possible points, this would seem like a higher score. But who performed better among their peers, then between the two of them, we know it's the other one. So between amongst them, the Z score of your friend is much higher. So we have like a Z, oops, 1 versus Z of 1.2. So we know that the friend performed better relative to their classmates. So between the two groups, um, among themselves, this is 85%. The first one is 85%. Okay, second one is much lower, but standardizing the score, the other one seemed to perform better. Okay, so let's talk about standardizing or standard normal distribution. Okay, let's take a look at this. When you say standard normal distribution, it's a normal distribution like any other normal distribution. However, a standardized or a standard normal distribution has a center at 0 and a mean of 0 and a standard deviation of 1. So let me just highlight that. So formula wise, we write that as 0, 1, which is actually here apparently. If variable x has a normal distribution of n mu sigma, so you have a mean of mu and a standard deviation of sigma, we can standardize using this formula. We kind of like wrote that earlier. Score minus the mean over the standard deviation. That gives you what we call a z-score. That is pronounced as z-score. And this picture here is an example of a standard normal distribution. Okay, you could see the mean is 0 and the sigma is 1. The standard deviation is 1, which is essentially what happened here. We kind of converted both of them into a standard normal distribution of 0 center. One of them has a z-score of 1, while the other one has a z-score of 1.2. Okay, so one is much further away than the other, but they're now sharing a similar scale. So they're now scaled up there. Even though their original scores are different, we can now compare them relative to each other through a similar scale. Make sense? All right, so let's see. Use the empirical rule Do you remember the empirical rule? 68, 95, 99.7. So let's use the empirical rule to and the standard normal curve to answer the following question. Okay, so first, this is 68, 95, 99.7. What is the probability? What is the probability, that's the P there, uh, or the area under the curve between z equals -1 and z equals 1. So remember, in a standardized normal distribution, we're looking at this part here from z equals -1 to 1. Anyone who knows that? We're looking for that one. Isn't that around for standard deviation? Within one standard deviation, so that has to be 68%. Yeah. How about more than one? So more than one. So the second problem is z is more than 1. Okay, let's go back here and let me erase this. So we're only looking at this thing here. Okay, that's more than 1. You say this is P, z is more than 1, okay, which is this problem here. Okay, so if you look at that, we can trust, well, one, you can, I know I have it here. You can have like a cheat sheet like that and kind of like add these things here.
Is it
Um,
16%?
how much was it?
16%.
16? Okay. Did we have like a similar, I think we had a similar question like this last time too, right? When we subtracted something from 50%. So let's see, 16%. And let's double check, especially if you kind of forgot about that. So we know that here, I think it is 16%, yeah. So this is 34% because both of these 34% make up 68% of the typical values. So you do 100%, take away 34%. I mean, not 100%, sorry about that, 50%, half. So half, which is from here onwards, this section here, 50% of the data minus 34% here gives you 16%. Yes, you're right. So you could see it's a dramatic decrease. This is 34%, the remaining beyond one standard deviation is only 16% left. From -2 to 2, I think even without the drawing, we can answer this.
95%.
Correct. So from second standard deviation, within second standard deviation, above and below, -2 and +2, um, that's essentially 16%. Okay, good. Okay, so another one. Suppose that the distribution of chicken eggs, very relevant. Um, Chicken egg weights is normal. So we're looking at different eggs, and the data, if you collect all the eggs, it's a normal distribution. The given weight, average weight is zero point 0.2 ounces and a standard deviation of zero point 0.3 ounces. The minimum weight of a jumbo egg is 2.5 ounces. Okay. And that's the story. So we have a couple of chicken eggs. They are normally distributed. The weights are normally distributed. The mean is 2. You can find it at the center. Standard deviation is zero point 0.3. So you can expect the spread to be zero point 0.3 from the center. It spreads out around 0.3 each time. And the minimum weight of a jumbo egg is 2.5. So it's right there. Actually, this one, I want to delete this box. And then like annoying. Oh yeah, there you go. Sorry about that. So we're kind of like given the x here already. That's around 2.5. What is the z-score for the smallest jumbo egg? So this is the smallest one. Anything higher from 2.5 or higher are considered jumbo, like big eggs. Okay, so those are all jumbo eggs that you can find there. What is the z-score? Where does it start? How far is it from the center for it to be considered a jumbo egg? So that's essentially what the question is asking us about. What is the z-score of the smallest jumbo egg? Okay, so we know that the z is equal to x minus mu over sigma. We have all of them. They're all available for us. We know what the minimum amount is 2.5. Oops. Minus the mean, which is 2. And the standard deviation is 0.3. So let's see. So you have 0.5 over 0.3. Okay. That's around approximately 1.67, rounded off approximately. So it's infinite, non-terminating repeating decimal. If I'm not mistaken, I'm double check quick. 0.5 divided by 0.3. Yeah, it is. Okay, so what does that mean? So from the center, it's 1.67 standard deviation away. So it's not even 2 standard deviation away. So a jumbo egg, an egg is considered jumbo in terms of weight if it's an egg that is 1.67 standard deviation higher compared to the average weight of an egg, which is 2 ounces. Make sense? Okay, let's take a look at the next one. If you don't have questions, we can move to the next page and let me know if you have some questions. If you're following from your handbook, feel free to copy them. Oh, I kind of like did not see this number here. Sorry about the last one here. I kind of forgot about that. So if you look at this, we're looking at this one. That will give us around 2.5% because we know beyond 2 standard deviation, um, we only have like 5% to spare because there's 95% here, which means the last 5% has to be shared by the tail. Okay. Alrighty. So that kind of is 2.5%. Let's take a look at the, oh, we're still there, the chicken egg problem. Okay, so what is the probability that a randomly selected classified that a randomly selected egg is classified a jumbo? So this is no longer a z-score question because the question is a probability question. It's looking for a p value. So we're looking for an actual probability over there. So we're looking at the amount of shaded space here. Oh, we use StatCrunch and the normal curve to estimate the probability. Okay, let's see. Let me just go to our StatCrunch. I don't kind of open it earlier. Maybe this one. Can you see the StatCrunch
Yes.
screen? Okay. So to be able to get the p-value, that is considered a calculation. So we go to stat instead of graph. You won't see normal distribution here, but you can calculate normal distribution using a calculator. So calculator normal is right here. See that? So, oops. If you click that, you'll get a normal distribution like this. and it's already standardized. Okay. All right, so we have a mean. For our case, I think our mean was 2. And the standard deviation, was it 0.3? I think it was 0.3 for, the egg. And we're looking for the probability that it's jumbo. So I think jumbo egg was 2.5. Was it 2.5?
Yes.
2.5. And we want it to be more than, so the value x has to be greater than. Okay, there you go. So I duplicated the picture that was shown to us. You notice on top of it, there is standard, there's between, and there's 68, 95, 99.7. There's the empirical rule. So if you click the empirical rule, it will automatically convert it with using the 68, I mean the 2, the 2.3, 2.6. So it spreads out by 2.3 standard deviation. Now this portion already gave us the answer. So you could see at the probability row, it's 0.04779 or 0.047 or 0.05, 5%. So we can say that's 5%. Let me just go back to our discussion. So this thing here is approximately 0.047 or 4.7%, almost 5%. Okay. So fill the missing values and label the probability in the image. I think the mean was 2. Standard deviation is 0.3. This is 2.5. 2.5 here. These things. And this is approximately around 0.047. And X here represents the weight of the chicken egg. Okay. Well, jumbo chicken egg. Okay. Any question about that one? So how to use StatCrunch? Quick summary. We go back to that screen if you don't mind. Go to Stat and go to Calculator and pick normal and just start entering the mean, the standard deviation, your value for X. This one will give you the P before you hit compute. Now choose whether you're looking at above or below the mean, because that's going to be different portion of the shaded area. A little bit, another option you can have here is if you choose between, then you can enter what's the area between -1 to 1, for example. We know that's 68%. That's why it's 0.68. For -2 to 2, we know that's around 95%. So we can actually calculate areas in between as well. And that's around 95%, 0.9544997 to be exact. Okay, so very, very useful, especially for your project. And at the very end of the semester, where you need to calculate the p-values. This is one of the, what we call a p-value, your probability value over there. Ready, let's see, letter C. We have a letter C. Now find the probability again. So we're looking for another p-value. It's my highlighter. Okay, there we go. So we're looking for another p-value using the StatCrunch again. But this time, enter the mean and standard deviation For the probability distribution of egg weights, as we have done before, fill in the missing values and label the probability in the image. Uh, I think we kind of did this already. Did we actually? Oh, we did it ahead of schedule. So sorry about that. This is actually letter C. Okay. So I guess here it's gonna be the same answer, but let's see. Uh, yeah, this one kind of like is a different value though. It's 1 point something. Yeah. So I think we did it ahead of schedule. I'm sorry about that. I really don't know what this is. Is it 1.5? Because it's not in the problem. Yeah. I guess it wants us to just try it. I guess this is more of a trial thing. Uh, I would say that's around more than 1.5. The mean here is 0, and the standard deviation is 1. And that's around, let's say, that's x equals 1.6, maybe. This is from a previous example, from here, maybe. Because we got here a z of 1.67. You should still be able to get the same answer. We got 0.047, I think. Was that it? All right, so I guess we can skip this one because I kind of spoiled it already for everyone. We already answered that one. Okay, so why do we teach z-score and standard normal distribution when we really don't need to find probability? The answer is the z-score. What we're doing right now, they're all pillars. They're all upcoming, like building blocks for upcoming lesson. For now, we did kind of compute the probability. However, in general, we use the z-scores much, much later in the course, and we're kind of like looking at it early on. So you have an idea what it is. And this is most useful in statistical inferences methods when we try to extend or interpret what we got from a sample. So of course, if you're looking at a certain population, in most cases, it's harder to actually gather data from everybody there. Just people alone, there's like 7 billion people in the world. You can only get a little bit in it. You can only get a sample from it. Now, from the sample, we will make inferences. We will actually do not just a more sophisticated educational guess to interpret the whole population, and that will be very useful for that. um, Standardizing scores is your first look, your introduction on what we call a test statistic. So z-score is a type of test statistic. There's a bunch of them, and the standard normal curve is the first example of a density curve or the distribution that is based on test statistic. Okay, so you could see when we have uh, our standardized normal distribution, which is centered at 0, and a standard deviation of 1. Um, any measurements that we find there is considered test statistic when we convert it to z. Okay. All right. Any questions so far? That is the main objective for the day. Now, let me see how many are in the room right now. So there's 14 of you. I will stop recording in a few. Let's try to group together. So if you have your handbooks with you, we'll just answer one page for today. Well, it's just the only remaining page for this module. I check it ahead of time. But I wanted to try a breakout session. I'm going to be online to monitor everyone. And if you need help, um, I'm going to stop recording and I'm going to group you through breakout rooms. And we'll probably group into three. Uh, oh, it's 14. We can have maybe three groups, like five, and four, in the breakout rooms. Okay, so let me just stop recording.